Now, a few more quick examples of modeling with differential equations. Right? So here is a very interesting scenario. So we're going to compute what initial velocity it requires to escape the Earth's gravitation. Well, so here a spacecraft is shot like a giant bullet, meaning that, well, we assume that there is no air, and we assume that the path of the spacecraft is perpendicular to the surface of the Earth, and that is not a rocket, right? So there is no acceleration, so it just has the initial velocity and then free flight. Okay. Then we have Newton's law of gravitation, right? So according to Newton's law of gravitation, the force of gravity is directly proportional to the product of masses of two bodies and inversely proportional to the square of the distances between the centers of the bodies, right? So which is why we have this equation. Maybe let me try to draw a picture. So if, say, if this is Earth, and suppose that this is our spacecraft, so that's our rocket, or whatever. Well, it's not a rocket, but anyway. Okay, so that's the distance between the spacecraft and the center of the Earth, and here x is the altitude, so the distance between the surface of the Earth and the spacecraft, and big R is the radius of the Earth. Well, note that Newton's law of gravitation is a second-order differential equation. So what can we do about it? And here is a very clever trick. So we're going to do a substitution. Right? So although in our second-order differential equation, what we have is that x is the unknown function or the dependent variable, and t is the independent variable. What we are going to do, we are going to kind of change it to something else. Right? So we are going to translate it to another equation where x becomes the independent variable, and the speed dv dt, sorry, dx dt, which is denoted as v, is going to become the dependent variable. Dependent variable or the unknown function. And well, you see how this is done. So if v is dx dt, then the second derivative of t is going to be dv dt, but at the same time, please look here, dv dt is dv dx times dx dt according to the chain rule. But then dx dt here is just v. So that's how we did it. So the second derivative of x is nothing else but dv dx times v. Well, and then when we substitute it to the equation, that's what we're going to get. So note that this trick In principle, it is applicable whenever we have any equation of the sort where the left-hand side is the second derivative of the unknown function, and the right-hand side is any expression containing the unknown function and its first derivative, but no independent variable t. So we were able to do it because there is no independent variable explicitly present in the equation. In other words, this trick would allow us to transform any autonomous second-order differential equation to a non-autonomous first-order differential equation. Well, but then if you look at it carefully, you will notice that this is a separable differential equation, and I challenge you to solve it and to answer this question: what initial velocity does it require to escape the Earth's gravitation? And of course, then you can check if your calculations are correct by just googling escape velocity. All right, so another example is this catenary curve. All right, so the catenary curve is the form assumed by hanging cables or ropes. It has this funny property that if you design the shape of the floor as many turned over catenary curves, then you will be able to ride along such floor on square wheels evenly, right? So the thing is that although the wheels are square, still at all times the seat here is on exactly the same height above the floor, which means that the person here is actually riding smoothly. So although the road is bumpy, but the motion is not bumpy, it's smooth. Okay. So, and again, note that this is technically a second order differential equation, but of course you can just introduce a new variable. So note that there is no y here explicitly present, so which means that what you can do is you can introduce a new variable, say u. If u is dy dx, then du dx is d2y dx2, and this equation becomes du dx equals a square root of 1 plus u square. This is also a separable differential equation, so we can try to solve it and find the shape of the catenary curve explicitly as a function of x. Oh, well, another very interesting real-life problem is to design the shape of the slide of the fastest descent. So what I want to imagine a sleigh on a slope, or in this case this was on Viva City, so Singapore kids, they just take trays from a nearby canteen and they slide from the slope. But the question is, if you suppose that you have the perfect slippery slope, so that there is no friction, then what is the shape of the slope so that the object would slide just by its own weight? It would slide down so that the descent is as quick as possible. And it turns out that the answer is neither a straight line nor a circle, and the whole process is described by this differential equation. So note that unlike most differential equations, this one does not have dy dx in the left hand side. So first you need to change it so that dy dx is in the left hand side, and then you can solve it, although it is not easy. But so you can just if you're interested in this, you can just Google